This segment is the second of two that contain a few bits of information about information theory, and we're going to work our way up to talking about mutual information. We were looking at the monographic and digraphic distribution of amino acids in human proteins. What that means is simply, as a function of amino acid, and there are 20 amino acids, they're listed down here, what is the probability of finding any given amino acid at a random position in the human proteome. And we learned that they vary over about an order of magnitude, from the most likely amino acid, leucine, with probability about 1/10, to the least likely amino acid, it's down here, tryptophan, with probability about 1%. We can also ask what we would find if we looked at consecutive pairs of amino acids in the human proteome, and that would be the digraphic distribution. And it's shown, at least graphically, over here for any given value of the first amino acid across the horizontal axis and the second amino acid immediately adjacent to it in the sequence. Down the rows here, we have a probability value here represented as a heat map, with white being more probable and black being 0. And if we added up all the 400 values here as individual probabilities, we would get 1, because every pair of consecutive amino acids has to be in one box or another. Now, we learned how to compute the entropy of these two distributions, and we found that the monographic entropy, the sum of p log p when you sum over the 20 amino acid probabilities, was 4.1908 bits. Whereas the digraphic probability, summing p log p over the 400 individual probability entries, came out 8.3542. which is slightly less than twice the monographic entropy. And what that shows is that there's some redundancy. In other words, given the first in the pair, the second in the pair is a little bit more predictable than it would otherwise have been. And that's what we're going to try to capture now in some equations. Recall that the digraph entropy is computed, as I just said, by a sum over all 400 values of I and j, and it's just p log p of those individual values. So it's flattened in the sense that it's not using any of the structure of the pij, the fact that p is actually a matrix here, not just a vector. And therefore it's lost this idea that I is the index of a first amino acid and j is the index of a second amino acid. And that's what we want to now recapture by defining something called the conditional entropy. So the conditional entropy, conceptually, is the average entropy of the second character given the first character. And what do we mean by average here? By average we mean, of course, averaged over the first character. So let's try to implement that. If we're given the first character, then here in this inner expression we're given a value of I, and we simply want to compute the entropy of the 20 possible choices of j. But to normalize those 20 probabilities, we have to take the pij's and divide by the pi dots. This is this notation where dot means sum. So pij over pi dot would be 20 numbers which sum to 1 and are the probabilities of seeing j given that we've seen I. And now I just take that expression and do the p log p thing, sum over j, and that gives me the entropy of one row. Now to take the expectation over rows, I simply sum over the rows I, weighting each one by how much total weight there is in that row, and that's pi dot, namely the sum over columns of the individual probabilities in the ith row. Well, you can simplify this expression. Take the sum j out to the outside. Now notice that we have a pi dot that cancels the pi dot here, and we simply get minus the sum over I and j, pij log of pij over pi dot. And that's the expression for the conditional entropy of the second character given the first. Now we can rewrite this in a couple of ways. We can take the log of the quotient and expand that as the sum of two logs. And the first one, the log pij, well, that combines with the pij log pij to just give us back the digraphic entropy right here, the entropy of x and y. And the next term, the pij log of pi dot, well, a minus sign comes from the fact that it's in the denominator, and there's a minus sign here, so it actually comes in here with a plus sign. And now if you do the sum over j first in that expression, because the thing in the log doesn't depend on j, we're just summing over the probabilities pij over j, and that gives a pi dot, and therefore we have the sum over I of pi dot log pi dot. And you can see that that's just the entropy of the first character. So we've learned something. We've learned that the conditional entropy, defined conceptually in this way, actually simply depends only on the monographic and digraphic entropies. In fact, it's the digraphic entropy, and then you subtract the monographic entropy. In fact, there are a bunch of other relations all like this that are easy to prove, and they can be summarized in this diagram here. And let me show you how you use this. Here's the digraphic entropy. That's a quantity of this magnitude. It's positive, so let's say this length. And we've just learned that the digraphic entropy is equal to the sum of the monographic entropy of x, that takes us over to here, and then I'm going to come down to here, plus the conditional entropy of y given x. So that's a very logical statement semantically. Similarly, the digraphic entropy is equal to the monographic entropy of y plus the conditional entropy of x given y. You'd have to go back and prove that, but the proof would be exactly the symmetrical proof of what we proved before. Well, in this diagram, there's something here in the middle that's called the mutual information, I of x and y. And it's defined basically, as you see here. Let's try to use this definition. The mutual information is the entropy of y minus the conditional entropy of y given x. You can see that here. It's the entropy of y minus the conditional entropy of y given x. Or we could do it on this side. We could say that it's the entropy of x minus the conditional entropy of x given y. And because all these things add up in these relations, those are consistent. Now if you go back to the definitions of these things and substitute in the p's and play around with it, you'll see that the mutual information, I of x and y, is actually this combination of things. It's the sum over I and j, all the pij's, but then what's in the log is pij in the numerator, and in the denominator the product of the marginals, pi dot and p dot j. You can see from the picture up here that mutual information measures the amount of dependency between two random variables. We've thought about dependency before in a number of other contexts. For example, when we were worrying whether two random variables were correlated and was the correlation statistically significant. Well, that was a particular kind of dependency, a kind of a straight line dependency. Here, the mutual information is the most general possible dependency. It simply says, given the value of 1, have you done anything to reduce the amount of uncertainty in the value of the other? How do I see that? Because h of x, the entropy of x up here, is the uncertainty in x, or equivalently the information content of x. And if there's this much mutual information, then the uncertainty in y, the information in y, is only the entropy of y given x, which is that much smaller than what the entropy of y by itself would have been up here. Now this diagram would only work if I, the mutual information, is always a positive number. And that is true. Let me show you one of these proofs, because information theory contains proofs that use this general idea all the time. So here's the definition of mutual information, and as I commented, it's equal to this, and this is actually written in the second row. Oops, this is minus the mutual information, and therefore, to make this minus, the numerator and denominator have been exchanged in the log, comparing this to this. Well, that was intentional, because now I'm going to use the inequality that says log of anything is always less than or equal to anything minus 1. So making that substitution here and putting the less than equal sign here, I continue by noting that the Pij cancels this Pij in the first term, and then the Pij multiplies 1 in the second term. But if I have a sum over I and j of p dot j and p dot I can just do the sum over I of pi dot, and that's going to be 1. And I can do the sum over j of p dot j, and that's going to be 1. And then here, it's the sum over I and j of Pij, and that's also going to be 1. So 1 minus 1 is 0, and therefore this thing is less than or equal to 0, and therefore the mutual information is greater than or equal to 0. So the picture always works. Now if we actually compute the numerical value of the mutual information for our example of amino acid monographic probability and digraphic probability, the answer comes out to be this: 2.66 centibits, about 2.7. And you might wonder whether something that's such a small fraction of a bit is ever important. And the answer is yes. It's important not because it's really giving all that much information about what the next amino acid is, but it's showing that there is a small dependency between the first and second amino acids. It's a signal there. And if you were asking the question, do consecutive amino acids depend on one another, it would be very easy to find this signal. And the way you tell how many characters of amino acid on average you would need for the signal to be, say, about 1 standard deviation, the answer is it's 1 over the number of bits in order of magnitude. 1 over 0.027 is about 40 characters. And the signal would be easily detectable in 100 characters, that is to say, in a protein of length 100 or more. Now we're going to go back to the racetrack, because mutual information has a particularly interesting interpretation in game theory, or put less abstractly, in betting on horses. Let me define something called side information. Suppose there's a horse race, and it has outcomes indexed by I, those are the individual horses, and each horse has a probability pi of winning the race. And we're going to assume this is not true in real life. We're going to assume that you can always bet at fair odds. That means if a horse's probability is pi, you can obtain odds of 1 over pi. That means you bet $1 and you'll win 1 over pi dollars if that horse I wins. Now what makes this interesting is that you also know the value of another feature, j, that is partly informative about the outcome of the race. In other words, what you know is a whole matrix of probabilities, namely for each column j, it tells you what the pi's would be under that side information j. And what's interesting is when your matrix Pij is not diagonal, because that would be the case of perfect prediction, nor is it rank 1, because that would be the case where your feature is completely independent of the outcome of the race and there's no information in it. So maybe this would be clear if I just give a little 2x2 example here. In this case, I, as I mentioned, is which horse is running in the race, and J is the side information that you know which jockey is going to be riding that horse. And here's an example where there are just two horses in the race. Secretariat, who's probably the most famous racehorse of all time, and some old nag who rarely wins the race. So the public sees betting odds over here of 95% chance that Secretariat will win and 5% chance that the old nag will win. Your side information is that you know which jockey is going to be riding old nag. Either some unknown is going to be riding old nag, or Willie Shoemaker is going to be riding old nag. Willie Shoemaker is the most famous jockey ever to have lived. Now, Willie Shoemaker is such a great jockey that if he's riding old nag, then old nag and Secretariat have equal chances of winning, 1%. But there's only a 2% chance that Willie Shoemaker will be riding old nag. 98% of the time, old nag will be run by some unknown, and then there's only a 94% chance that Secretariat will win and a 4% chance that old nag will win. Actually, I've said that wrong. It's 94 divided by 98 chance that Secretariat will win and 4 divided by 98 that old nag will win. The point is that these PIJs all add up to 1, and it's the marginals that are the probabilities of Secretariat and old nag winning unconditioned by the side information, and it's these marginals that are the probabilities of each jockey riding old nag. So now we've got that straight. And the question is, what's your best betting strategy in this situation? Now, for each value of J, that is to say your side information, you have to know how to divide up your bets between the two horses. That is to say, there's a whole matrix which is the fraction of assets that you bet on I when the side information is J. And these have to add up to 1 when summed over I. In other words, J just fixes the side information, and then Bij are the proportions of your assets that you bet on each horse, summing to 1. And we want to maximize the return on our assets per play. Now, our total assets may just be any number, so what we really want to do is we want to maximize the log of our return, because that would be the fractional increase of our assets depending on what the total amount is that we bet. So we want to maximize this quantity W, which is the expectation over basically everything. It's the expectation both of which horse wins and of which jockey is riding the horse, of how much we bet times the payoff on that bet. And the payoff is 1 over Pi dot. Do you see why it's Pi dot? It's these numbers here, because the payoff is simply determined by the overall probability of winning as seen by people who don't have your side information. Okay, well, back to this expectation is the sum over I and j, Pij times this log. And we want to find what are the values of Bij that maximize this. And we can do this by Lagrange multipliers. The Lagrangian is the thing we want to maximize, minus a set of constraints. And there are j constraints because each separate value of j up here, the bi's have to add up to 1. So the way you do that in Lagrange multipliers is you write down a separate Lagrange multiplier term for each constraint, and you add all of those terms into the Lagrangian, and so that's the sum over j here. And here's our constraint that the Bij summed over I must equal 1. So let's work it out. That's the same Lagrangian from the last page. We take the derivative of the Lagrangian with respect to some particular values ij, with respect to bij for those particular values of I and j. And you can see that the bij in this term occurs only here, and so that brings in a 1 over bij multiplied by the pij, so that's this right here. And here, a particular bij occurs only once in both of these sums, and that simply brings in a lambda j, which is here. So we get a very simple result for bij, don't we? We get that bij is proportional to pij. And the proportionality constant, which was the Lagrange multiplier, is obviously going to just be p dot j, because then that's what's going to make the normalization condition up here be satisfied. This is a very famous formula. It was first derived by Kelly, who was a colleague of Shannon, in 1956, and it's so-called Kelly's formula, but it's also called the proportional betting formula. And what it says is, you should always bet in linear proportion to the probabilities conditioned on any side information. That's not intuitive, because let's take the example down here. Suppose you know that Old Nag is being run by some unknown. Then you might have thought that you should just bet all your money on Secretariat, that that's the best outcome. But no, it's not. What Kelly's formula shows is that you should always place bets on all of the horses. This is assuming that there were no transaction costs that were added on. And you should place bets on all of the horses in proportion to your estimate of their probability of winning. So in this case, you would place your bets in the proportion of 4 to 94. And in this case, if you have the side information that Willie Shoemaker is the jockey, you would place, as you can see, even bets, half of your stake on each of the two horses. And that actually maximizes your winnings. And how much do you win? Well, the amount you win, expressed as a logarithm, in other words, your fractional return, is this value w, and w, if I put in the result I have for bij, turns out to be this. And look at that. It's exactly the mutual information. So your expected gain when you know something about the race, when you have some side information, is the mutual information between the outcome and your side information. How do you interpret the number? Well, for example, if the mutual information came out 0.1 nats, that is to say, measuring everything using natural logs, not logs base 2, 0.1 nats means 10% return on your capital for each race. And you can get pretty rich with that. Of course, it's stochastic. You don't always win, but this is your average logarithmic return for each race. In this particular example here, with Shoemaker and Old Nag, the mutual information turns out to be quite small. It turns out to be only about 1.75%, or 0.0175 nats. In that case, you'd have to have a lot of races going to show a large return, but on average, you'll gain 1.75% on your assets for every race run. Finally, let's turn to a different topic, not mutual information, but closely related. The Kobuk Lie Blur distance is an information theoretic measure of how different two distributions are. So one distribution is a set of probabilities pi, written as a vector here, and another is a set of probabilities qi, and it's assumed that there's the same number of p's as q's, and we want to know how different are those distributions, and the Kobuk Lie Blur distance answers that question by defining a distance with this expression. Now, this has at least one of the properties that you would expect for a distance. If the pi's and the qi's are exactly equal, then the argument of the logs are all 1, therefore the logs are all 0, and the distance is 0. It doesn't actually have the two other properties that we wish that a distance would have so as to be a metric. It's not symmetric between the p and q's. The d from q to p is one way of thinking about this. Is not the same as the distance from p to q, and you can see just because this expression is not symmetric. Well, you can't have everything. The Kobuk Lie Blur distance is always positive, and we can prove that it's this same inequality that logs satisfy, right, minus the Kobuk Lie Blur distance, which is therefore this thing where I've interchanged numerator and denominator inside the log, and log of anything is less than or equal to anything minus 1, and now this p cancels this pi cancels this pi, and I get the sum of the qi's, which is 1, and then for this term I get the sum of the pi's, which is 1, which is 0. Well, that's a relief. For a distance, at least, it's positive. So you might wonder if it doesn't obey symmetry, and by the way, I just should have said up here, it doesn't even have a triangle inequality. It's not a metric in the mathematical sense, but it turns out to be useful in a number of situations. So I'll give you a couple of interpretations where Kobuk Lie Blur comes in. Number one, it's the extra length needed to compress a message with characters drawn with probabilities p if you're mistakenly using a code designed for probabilities q. And let's see why that is. Because the characters in the message occur with probability pi, so your expectation over the message is the sum I over pi. But the lengths of the symbols that you're going to have to use to represent those characters coming from the code designed for qi is going to be the log of the probability qi on average. Okay, well, if you take this expression and add and subtract the right extra log, namely pi log pi, in the right way, you'll see that this expression is exactly the entropy of p, which is also the length of code you would have needed if you had been compressing with the correct probabilities, plus an extra piece, and that extra piece is exactly the Kobuk Lie Blur distance of p from q. Second interpretation. Suppose your hypothesis is that you're seeing values drawn with the distribution q, but you're actually seeing values drawn with the distribution p. How many characters do you have to draw before you can decide that you're seeing q rather than p? Well, we could do this by a Bayes odds test. We could ask, what's the ratio of the probability of the data given p versus the probability of the data given q? And as each character is drawn, if we have IID on the characters, which is being assumed here, then the probability of the data given p is multiplied by a value pi, whereas the probability of the data given q is multiplied by the value qi. So the quotient here becomes a product over all the individual draws, all the individual characters in the message, of each character's pi divided by qi. So that's the odds ratio for any particular sequence of i's that are observed. But what if I want to know in advance what I should expect that odds ratio to come out? In other words, in advance, given the distributions p and q, I want to know about how many characters I'm going to have to draw to distinguish between them. For example, I might want to know how many draws on average will it take to make the log odds, the log of the odds ratio, achieve some particular value, maybe 10 or 50. So now let's consider how the log odds change in expectation. Well, as each character is drawn, I'm going to get a pi over qi, and then I'm going to take the log of that. In other words, I'm substituting the sum of the logs for the product of the arguments here. But on average, that will occur just pi of the time. So I'll have a sum of pi, the expectation, times log of pi over qi. We'll look up here. That's exactly the Kobuk Lie Blur distance. And so we've seen that it is the average log odds per character of rejecting the false hypothesis. Finally, number 3. The Kobuk Lie Blur distance is your expected capital gain. We're back to the racetrack. When you can estimate the odds of a fair game better than the person offering those odds, and also when you bet by Kelly's formula. So let's see how that works. We're back to trying to maximize or find what W is. That's the expectation of the amount that we bet times the payoff of that amount. And it's the expectation, of course, over how often do we actually win. So here's that expectation. We win pi of the time if we've bet on I. And when we win, our log stake goes up by the log of the amount that we bet times the payoff. Now, we're going to use Kelly's formula, and so our bets, BI, depend on some estimates we have, QI, of the odds. In other words, in this case, nobody knows the real odds. We're trying to estimate them as QI, and the person offering the bet is trying to estimate them here as RI. How can I see that? Because they're offering a payoff on the bet of 1 over RI. So if I put QI in for BI and 1 over RI in for sigma I, and now compute that expectation over the true odds, PI, which are unknown to both of us, you can see that my expected payoff, if you manipulate this a little bit, can easily be seen to be the difference between two Kobuk Lie Blur distances. And look how that works. If my estimate Q is closer to the true odds than the bookie's estimate R is to the true odds, then this is positive and I win. But if it's the other way around, if the bookie is estimating the true odds better, then on average I'm going to lose. I'll let you work out the generalization of this to the case where the house, the racetrack, keeps a fraction 1 minus f, so that even if the bookie is offering fair odds, I'm only going to get a payback fraction f. And in that case, it turns out that not only do I have to exceed the bookie's accuracy in estimating the odds, but I have to exceed them by this certain amount, which is the house percentage on the bet. In summary, betting is a competition between you and the bookie on who can more accurately estimate true odds, and the measurement of accuracy is in fact the Kobuk Lie Blur distance between the distributions.